Here we have f of 0 is equal to 0, f prime of 0 is equal to 1. And then we have a formula for the rest of the derivatives. So f of n plus 1 of 0 is negative n times f to the n of 0 for all n greater than or equal to 1. So number 6 here, a function f has derivatives of all orders from negative 1 to 1. The derivatives of f satisfy the conditions above. The Maclaurin series for f converges to f of x for and the absolute value of x is less than 1. So within the radius of convergence is 1 is what they're saying. A, show that the first 4 non-zero terms of a Maclaurin series for f are as follows here, and write the general term of the Maclaurin series for f. Well, up here at letter A, we have f of 0 is 0, f prime of 0 is 1. That's the given. And then once we start at 1, the second derivative is negative 1 times the first derivative of 0. So that's negative 1 times 1. So this is the negative 1 right here, and then the previous is 1. So negative 1 times 1 is negative 1. Then the third derivative is the previous derivative times negative 1. So where's that? Let's see. Negative 2, and then times the previous is negative 1. That's positive 2. So then the fourth derivative is negative 3 times the previous, which is 2. So now we have all the derivatives. Well, the first is 0, so it starts out with 0. Then plus 1x minus 1x squared over 2 factorial plus 2x to the third over 3 factorial, and then the minus 6x to the fourth over 4 factorial. And then when you simplify, you see that 1, 2, 6, those are factorials, but they're lagging behind by 1. So that cancels out most of the factorial, just leaving the last number. So the general term is negative 1 to the n plus 1 because it's alternating, and then x to the n over n. Here's the next one. Determine whether the Maclaurin series described in part A converges absolutely, converges conditionally, or diverges at x equals 1, and explain your reasoning. Well, we just need to show the work here. So when we plug in 1 into the x over here, we just get 1 over n. Now, if we take the absolute value of this, it becomes the alternating, or not, it becomes the harmonic series. So the harmonic series diverges, and then if we go back to the original to see if it converges conditionally, it does converge conditionally by the alternating harmonic series. So there it is. Write the first 4 non-zero terms in the general term of the Maclaurin series for the integral. So I just took term by term integration of kind of the final answer in part A. So here we have 1/2 x squared, 1/6 x to the third, 1/12 x to the fourth, 1/20 x to the fifth right there. Now, the pattern is down at the bottom here, this is 1 times 2. This is 2 times 3, 3 times 4, and 4 times 5. Let me turn this down just a little bit. Here we go. That should be better levels. Anyway, so it's alternating. So negative 1 to the n plus 1. X to the n plus 1 over n times n plus 1. That's that 1 times 2, 2 times 3, 3 times 4, and so on. Letter D, let p sub n of 1/2 represent the nth degree Taylor polynomial for g about x equals 0, evaluated at x equals 1/2, where g is the function defined in part C. Use the alternating series error bound to show that the 4th degree polynomial of 1/2 minus the actual value, so this is approximation minus the actual value, that's error, is less than 1 over 500. So the remainder, or the error, is less than or equal to, now we need the next term. And the next term would be right here. Here it is. Right there. So negative 1/20th, 1/2 to the fifth, because we're evaluating at 1/2, is less than or equal to 1 over 2 to the fifth is 32. Those multiply to 64, and that's less than 1 over 500. Here's the rubric. 1 for the derivatives, 1 for verified terms, 1 for the general term. Here we have 2 for converges conditionally with reason. Letter C, 1 point for 2 terms, 1 for the remaining terms, and then 1 for the general term. And then finally, letter D, 1 for the error bound, kind of the process. You have to show the process. The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 is 1, f prime of 1 is negative 1/2, and the nth derivative of f at x equals 1 is given by this messy function here. Let me shade it so that we can kind of see each part one at a time. Oh, I guess I got to go. I put the work down at the bottom. A, write the first four non-zero terms in the general term of the Taylor series for f about x equals 1. So here's the givens, the 1 and the negative 1/2. Now if we plug in 2, the second derivative, we have negative 1 squared. That's going to be positive. Then 2 minus 1 factorial is 1 factorial over 2 squared. And then when we plug 3 in, we get negative 1 to the third, 2 factorial over 2 to the third. Now when we plug all this into the polynomial, we get 1 minus 1/2 times x minus 1, then 1 factorial over 2 factorial. Well, those factorials, these two combined just go to the number 2. 1 factorial just being 1. Then 2 factorial over 3 factorial would just give you 3 here. And then the next one would just be 4 in the denominator. The next one would just be 5 in the denominator. So here it is all cleaned up a little bit, leaving the 2's. I could have wrote this as 4 and this is 8, but it's really 2 to the n. So it's negative 1 to the n, x minus 1 to the n, because we're starting everything with a power of 0. 2 to the n, and then times n, times 0, well, not really times 0 there, but times 1, times 2, times 3. If we wrote this with sigma notation, we'd have to do this. We'd have to have 1 minus n equals 1 to infinity of, then we'd have negative 1 to the n, and that, I guess that'd be plus, because that would give you the negative x minus 1 to the n over 2 to the n times n, because this 0 multiplying by 0 in the denominator would really mess things up. So this is the general term, except for, it doesn't fit giving the first term, so we'd have to write this a little different with sigma notation. A letter B, we have, well, let's see, what does it say? The Taylor series for f about x equals 1 has a radius of convergence of 2. So centered at 1 with a radius of convergence of 2. So we could write it like this. Negative 2 is less than x minus 1 is less than 2. So when we add 1, we get negative 1 is less than x is less than 3. So we're going from negative 1 to 3 just by that first sentence. Find the interval of convergence and show the work that leads to your answer. So now we have to plug negative 1 into the general term. And when we plug negative 1 in right here, we get negative 2. So there's the negative 2 that you get when you plug negative 1 in. Now, negative 2 to the n over 2 to the n is negative 1 to the n, right there. Well, negative 1 to the n times negative 1 to the n is negative 1 to the 2n. When you have the same bases, you add the powers over n. Well, that's going to be even, so a negative 2 in even is just going to be positive. So this diverges by harmonic series. With x equals 3, when we plug 3 in for this x, 3 minus 1 is 2, so 2 to the n over 2 to the n, that becomes 1. So this converges by alternating harmonic series. So the interval convergence does not include negative 1, but does include 3. Letter C, the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So here's 1.2 plugged in, and 1.2 minus 1 is 0.2. So you get 0.905. Now show that the approximation found in part C is within 0.001 of the exact value of f of 1.2. Well, that's 1/1000th, by the way. So the remainder is, let's see, where's negative? How do we get negative 124? That is actually right here, 8 times 3. We're going to use this term right there. And so we have negative 1/24 times 0.2 to the third. That's 1/24 times 1/5 to the third, and 5 to the third is 125. So 125 times 24 is 3,000. That's less than or equal to 1/3000, which is less than 1/1000. So here's the rubric. There's the points, first two terms, third term, fourth term, and general term. 1 identifies both endpoints in one analysis and interval of convergence. 1 for the approximation, then 1 for the error form, and then 1 for the actual analysis. So 1 for this right here, and then analyzing it.